We can also estimate the truncation error using Taylor series. In other words, we can find the derivative term using the known functions that we showed in the previous slide. It is similar to that. The difference between the functions will provide us an information about the remainder term value. And we will show this in an example, in the parachutist example. And if you remember, we used the Euler method for this, and it is actually similar to Taylor expansion. I will show how it is similar. So if we write Taylor expansion, and if we try to adapt this to parachutist example where we wanted to find the velocity value. So our function f is actually the velocity now, and our x is the time now here. Ti plus 1, and this is equivalent to Vti, the first value, plus the derivative, the second term, the derivative of velocity function, times the step size. And the step size, we already defined this in the parachutist example as Ti plus 1 minus Ti, and it's just h value here, we can say, plus in the second term we have the second derivative, 2 factorial, and h square. H is again Ti plus 1 minus Ti and square of this. And if we continue, we will, if we cut at some point, we will have the remainder term, Rn. So let's truncate from the first, after the first term. So let's truncate here. With this truncation, we will have the first order Taylor expansion, and that is basically Vti plus 1 equals Vti plus derivative of Vti and Ti plus 1 minus Ti plus R1. So the remainder term is here now. And you know that this, especially this part, is the Euler's method that we already mentioned in chapter 1. And you can see that the first order Taylor expansion is equivalent to the Euler's method. Now, what we want to do is, actually, we said that we want to predict the derivative. So this is the derivative, and we want to predict that. We will isolate it. Let's isolate Vi. V prime Ti, sorry. If we isolate this, it becomes Vti plus 1 minus this value, Vti, and we will divide with this step size, this value, Ti plus 1 minus Ti. Of course, we will have the remainder term as well as the plus, but this will go over here and change the sign, so R1, and also we need to divide it by Ti plus 1 for consistency of the equation. Now we can have an approximation for the derivative, as you can see here. And the first term, this one, is called the first order approximation of the derivative. Of the derivative, and the remainder term is the truncation error, and this one, let's have this in a circle, this is the truncation error. So if we want to have this truncation error with the formulation that we know of, the R1 value from the general formulation of the R1, actually, we know that R1 is equivalent to, so because we cut it from the first term here, R1, we showed this already in the previous slide at the last comment, that the first R1 is the prediction of R1 is actually the second derivative of function with this symbol, because this was the prediction, 2 factorial, and here the step size ti plus 1 minus ti. So this is and of course it's the square, but here you can see that we have a division by the step size. So if we divide by step size over here, then we will have R1 divided by ti minus 1 minus ti. Here as well, if we divide this by that, ti plus 1 minus ti, this will be cancelled out by this, and that's why we will have, let me erase these, we will have just the first order of the step size. So if we summarize this again, R1 divided by h is equivalent to the second derivative, 2 factorial, and h. You can see that the R1 is actually, let's say, or R1 is in the magnitude of h only, because over here we have only h for the magnitude. This means that the truncation error order is just h, or ti plus 1 minus ti to the power 1, which means halving the step size. That means halving the step size, for example, will have the same effect on the prediction, meaning halves the error of the derivative. Therefore, it is important to use smaller step sizes to be able to have more accurate results of the derivative. So with this, you can see we can actually have a prediction of the first derivative, and also we see that the first derivative with the first order approximation have an error order of only h to the power 1, and halving the step size will halve the error of the derivative. We will talk about these derivatives in a later section, in this section, in later slides, in more details. And for now, this is the information that we know about how to predict the derivative.